Welcome back, students. Today we're going to be looking at another problem that we see in graph theory, and that's called finding the shortest route. All right, so think about if you were to reach into your pocket and pull out your phone and type in for directions to get from here to Indianapolis. All right, this is a very oversimplified explanation for what your phone, for what that computer is doing inside of your phone to determine that shortest route. All right, so what we're going to do is we're going to use a mathematician. His last name is Dijkstra. We're going to use Dijkstra's algorithm in order to come up with the shortest route. Now, notice that I'm saying route and I'm not saying circuit because this is not going to be a circuit. We are just going to go from wherever we're starting and we're going to get to our destination. All right, we're not talking about going back home. All right, so that means that we are going to start and end on different vertices. We're also not necessarily going to use every edge. We probably won't be using every edge because think about all the roads that exist from Rushville to Indianapolis. You're not going to drive on all of those. All right, and we're also not necessarily going to use every vertex. All right, because there are several cities to go from Rushville to Indianapolis. You have Arlington, you have Morristown, you have New Pal, but you could also say Shelbyville could get you from Rushville. So could Manila, so could Homer, and so on. So whatever you decide on for your shortest route, all right, you may or may not be using all of those vertices. All right, so Dijkstra's algorithm. You're going to start off with your starting vertex. You can either put a 0 by it or you can put an S for start. And then what he did is he suggested that you put an infinity symbol by all of the other vertices. And if that infinity symbol remains, it means that it's not going to be a part of your path. And even if it doesn't remain in the end, it might not be a part of your shortest path. All right, but it means that if you've changed it from an infinity to some other number, it means that it's become a possibility for being on your shortest route. And then you're going to look at your graph and you're going to figure out, okay, what vertices are adjacent to the start. And then you're going to list the distance. Okay, most likely this is going to represent distance, but I guess it could also represent cost or time or something else, but these are weighted graphs. So you're going to then list what is the weight to go from start to that next vertex. You're going to cross out the infinity symbol and you're going to write in what that number is. So then you're going to darken the edge that represents the shortest weight or the smallest weight. And then you're going to look at your graph. Okay, you're going to actually travel there. You're going to look at your graph and then you're going to figure out, okay, from here, where can I go? And then you're going to do the same thing. You're going to cross out the infinity symbols and you're going to put, okay, what would be the distance to go then from here? Okay, and then you're going to darken the edge that's going to be the smallest number that is associated with that vertex that you haven't yet been to. And you're going to keep repeating this process until you get to your end. Okay, and then you're going to look back at the graph overall and you're going to list your paths that lead from your starting vertex to the ending vertex. All right, and that's going to give you your shortest path. And then you're going to add up the weights for every edge that's along that path. And you're going to state how long it is. All right, so there are the directions. There's the algorithm. Now let's actually see that algorithm in play with a couple of examples. All right, so for this example, we have a graph that has 1, 2, 3, 4, 5, 6 vertices. So we might not necessarily go to all of these vertices except for the fact that I don't know where I'm going to end. All right, so what I'm going to do is I'm going to look at all of the possible scenarios. All right, so what's the shortest path from A to B, A to C? Okay, so what this is telling me is that we're starting off at A. So what I'm going to do is I'm going to either put a 0, okay, saying that we're starting here. Okay, there's 0 distance before it, or I'm going to put an S for start. It's up to you. All right, I think I'm going to go ahead and put a 0. All right, and then we're going to look at to see what vertices are adjacent to A. So we have B and we have C that's adjacent to A. So what I'm going to do, I guess before that, is I'm going to go ahead and put an infinity symbol next to all of these vertices. All right, so now going back to the vertices that are adjacent to A, we have B, and we have C. So what that means is from A, I could travel to either of these, which means that no longer is their distance to infinity. Okay, now we actually have ways to get there. So I'm going to cross this out, and I'm going to take whatever the previous vertex, whatever the number associated with it was, I'm going to take it and I'm going to add it with this weight for this edge. All right, so 0 plus 2 is obviously going to give me 2, and 0 plus 4 is going to give me 4. All right, so now I'm going to choose the one that's smaller. All right, so A to C, that's the smaller. So I'm going to go ahead and I'm going to darken this edge right here. So now I'm at vertex C, and I want to see what vertices are adjacent to vertex C that I have not already been to. All right, so I've already been to A. Okay, so now I'm at C. What vertices are adjacent to C? I have B, D, and E. So now what I'm going to do is I'm going to figure out, okay, well, what would be the total distance now to get to these vertices? All right, so if I'm going to go to C next, this previous distance to get to C was 2, and now this new distance from C to E, this new weight is 10, so 2 plus 10, this would give me 12. So I'm going to cross out the infinity symbol, and I'm going to mark down 12. To go to D, again, to get to C was 2, but now to go from C to D is 8, so 2 plus 8 is going to give me 10. And to go to B, okay, to get to C first was 2. 2 plus the new weight to go from C to B is 1. So 2 plus 1 is going to give me 3. So I'm actually going to cross out 4 because I've now come up with a smaller number. If this number had been larger, I would not cross it out, and I would actually go back and backtrack and use the smaller route, the shorter distance. All right. However, this is a smaller route, and so that means I'm going to cross out that number and I'm going to replace it with something that's smaller. Never going to replace it with something that's larger. So now what I'm going to do is I'm going to look at these vertices that I now have the option to go to. I'm going to look at the numbers associated with them, and I'm going to choose the one that is the smallest. So 3, 10, or 12, obviously 3 is the smallest. So now I'm going to darken the edge that goes from C to B. And now I'm at B. And now I'm going to look to see, okay, where can B go? So B is only adjacent to D. Well, it's also adjacent to A and C, but we've already been there. We've already figured out the shortest route to A. We've already figured out the shortest route to C. So now the only adjacent vertex that we have not figured out what the shortest route to it is yet, the one that we haven't yet visited because there's no edge leading to it, is D. All right, so B to get there was 3. The weight from B to D is 5, so 3 plus 5 is 8, which is in fact smaller than what we had before. So we're going to go ahead and cross out the 10, and we're going to mark down an 8. All right, so now we're going to look to see these vertices that we don't yet have an edge darkened to, that we haven't yet visited. Okay, these vertices. Okay, so I haven't done Z yet because it still has the infinity symbol with it. Okay, but E has been crossed out and we have a 12. D has been crossed out. We have an 8. We're going to compare those two. Which one's smaller? We have 8. We have 12. This one's smaller. So how did we get this number 8? All right, well, we went A, C, B, and then B would lead us to the D. So I'm going to go ahead and darken that edge. All right, and then from D, the only vertices we have not yet been to are Z and E. All right, so D was 8 to get there, and then 8 plus 2 is going to give me 10. So this is actually going to cross out the 12, and I'm going to replace it with a smaller possible route to give me 10. And 8 plus 6 obviously is 14, which is smaller than infinity. So I'm going to cross out the infinity, and I'm going to go ahead and put 14. All right, so which one is smaller of these vertices we haven't yet been to? And we have 10 and 14, and obviously 10 is smaller. So I'm going to go, how did we get 10? Well, it was from this route, A, C, B, D, and then that leads us to E. All right, and so then now the only possibility that we might have is E to Z. Is there a shorter route? So E to Z is 3. 3 plus what it took to get to E to begin with was 10. 10 plus 3 gives us 13. So we're going to cross out the 14, and we're going to replace it with 13. All right, and this is the only vertex we have yet to go to. And so we're going to now highlight the path that got us the value of 13. All right, so now we've done all the work. Now we need to take a step back from our graph, and we're going to look at it now overall as a whole. All right, so now I've figured out the shortest path to go from A to any of the other vertices. So now over here in my table, usually you won't have to list them all out. You'll only have one specific vertex that you're trying to end at. All right, but here I'm going to list out all of my shortest paths based now just looking back at my graph and all of the work I've already done. So if I had been trying to go from A to B, okay, remember graphs are not drawn to scale at all. The shortest route from A to B, all right, I'm going to follow my darkened edges to go from A to B, and that was A to C to B. So I'm going to go ahead and list that out. So it was, it was A and then to C to B. All right, so the shortest path to go to B was actually ACB, and that total length was 3. I can either go back and add, or I should already have the number right next to the vertex. Had I tried to end at C, all right, the shortest route from A to C was just going directly from A to C. So I just list where I started, any vertex in between, which there wasn't, and then my ending vertex, and then that route was a length of 2. To go from A to D, again, I'm just going to find that darkened edges that gets me to D. So that was ACBD. So ACBD. And that total weight up here was 8. To go to E, so here's E, follow the darkened edge, and that was ACBDE, and its total weight was 10. And then the last possible path from A to Z is just ACBDE, and that total weight was 13. All right, so there we go. This is the entire problem, all that we can do with the shortest route. Normally, again, you won't be doing all of these, but had you been asked to do all of them, we have now figured out the shortest path to go from this starting vertex to all of the other vertices in the graph. All right, so here we have another example. I have it set up for us already. We're going to start off with A, and then we're going to figure out what's the shortest path to all of the other vertices. So if we're starting off with A is only adjacent to B and C. So what I'm going to do is I'm going to cross off the infinity symbol, and I'm going to put what's the route to get there. So 0 plus 2 is going to give me 2 for B, and 0 plus 8 is going to give me 8 for C. And then I compare which one's smaller, 2 or 8. So obviously 2 is smaller, so I'm going to darken that edge. All right, and then B is adjacent to C. It's also adjacent to E. So 2 plus 5, that's going to give me 7. All right, so that's smaller than 8. So I'm going to go ahead and cross out the 8 and replace that with a 7. I found the shorter way to get from A to C, and that's to go through B. And then E is 7. So 7 plus 2, that's going to give me 9, which obviously is smaller than infinity. All right, so now I compare 7 or 9. Which one's smaller? 7's smaller. And so I'm going to darken the edge that gets me there. All right, so now I'm at C. I've already been to A and B. So what's C adjacent to that we haven't yet been to? And that is D and E. All right, so D is infinity, so something's going to be smaller than that, and that something is going to be 7 plus 4, which is going to give me 11. And for E, we have 7 plus 5, which is going to give me 12, but 12 is not larger than 9, so I'm not going to replace it. All right, so now I'm going to compare these two, 11 or 9. Which one's smaller? 9's smaller, so how did I come up with 9? All right, it actually wasn't connecting C to E. Okay, that would have given me 12. How did I get 9 before? Well, that was A, B to E. So I'm going to actually go back to B, and I'm going to darken the edge from B to E. All right, so now I'm at vertex E. I've already been to A, B, and C before it. So now I'm at E. What is E adjacent to that we haven't yet, that we don't have a path yet to get to D, or to F, or to G? All right, so I'm going to take 9 plus 4, and I'm going to add those together to give me 13, but I'm not going to change 11. I'm never going to change a number to something that's larger. All right, so now I'm going to look at G, which is infinity still, so anything smaller than infinity. 9 plus 5 is going to give me 14, so I'm going to cross that out. I'm going to put a 14. And then, well, that's it. Okay, E was only adjacent to D and G. So now I'm going to compare 11 or 14. Which one's smaller? Well, 11's smaller. How did I get the 11? It wasn't taking 9 plus 4. That gave me 13. So going back, how did I get 11? Well, that was by going from 7 plus 4 to give me 11. So that means I'm going to backtrack, and I get back to C, and that's going from C to D. All right, so then D. Okay, D was 11. We've already been to E. Okay, so now we're going to look at any other vertex that's adjacent to D that we haven't been to yet, and that's F. So we're going to take 11 plus 4, and that's going to give us 15. So we're going to cross out the infinity symbol. We're going to play down 15. All right, and then we're going to compare 15 or 14. 15 is obviously larger. We want the smaller number, so we have 14. How did we get 14? Well, that was by taking E to G. 9 plus the 5 is what gave us the 14. So backtrack, get back to E, and now we're going to darken the edge from E to G. And then the only vertex that we don't yet have a path to is F, which is 15. 14 plus 1 is 15. All right, so we can either get 15 by going this way, or we already had the number 15, which meant that it was by going from D to F, which is this. All right, so if they're the same, okay, that means that you can choose a route arbitrarily, or you could just put both of them down to list that there's more than one route that's the shortest route. There's a tie. All right, so now all the work is done. Now I'm going to take a step back from it, and I'm going to analyze, and I'm going to put the shortest paths from A to all of the other vertices. All right, so the shortest path from A to B was in fact just A to B, and that length was 2. The shortest route to C, well, we know the length for it is 7 because that's the number associated with that vertex. How did we get 7? We're going to go back and we're going to follow the darkened path. So that's A, B, C. All right, and then to get to D, which is up here, how did we get to D? Well, that was A, B, C, D. And that length was 11. How did we get to E? Well, that was from A, B to E, and that length was 9. How do we get to F? Okay, there were actually 2 routes. Okay, notice that we have 2 routes from A that get us all the way to F. All right, so I'm going to list both of those. That's either A, B, C, D, F, or A, B, E, G, F. Either way was a weight of 15. And then to get to G, don't be confused here. It's not A, B, C, D, F, because that would have given us 15 plus the 1 more to give us 16. No, the way that we got this 14 was by coming from E earlier. So that's going to be A, B, E, G. And again, that weight, G, that weight is 14. All right, so there we go. Again, you're probably not going to have to fill all of this out, but now we have examined the shortest path, the shortest route to each vertex. You might be wondering, that's quite a bit of work. I probably could have just done some trial and error and figured this out on my own in a lot faster method. The reason why there has to be an algorithm is because think of it as if you were a computer scientist. All right, these graphs that I've chosen for you are relatively small graphs, okay? Because the big graphs we leave to computers. All right, so how are you going to be able to program a computer? Well, you have to tell it what to do, okay? Computers are very, very, very smart machines, but they're actually only as smart as the person that is programming them. So you have to be able to tell the computer what to do, so you need a method. All right, so the computer wouldn't be able to look at this problem as a whole and then figure out, okay, what's the shortest route? Instead, it needs to be given a step-by-step algorithm, a step-by-step list of what it needs to do after what. And that is why we need to follow this algorithm. And so for your homework assignments or on your quiz, please make sure that you are showing this work. It's not that much work to show, but I will be looking to see, did you follow the algorithm or did you cheat and just look at it as a human and be like, okay, well, I can see the shortest route from A to C isn't just 8. It's going to be 2 plus 5, which gives me the 7, and so on. So please make sure that you are following Dijkstra's algorithm. All right, we have one more example, and that's going to be for a directed graph. Okay, a digraph, a directed graph. And the reason why this is a digraph is because these edges have arrows, which means that we can't go from A to B and back to A because this arrow is saying A only leads to B. B only goes to C, E, and D. D only goes to A and E, and so on. All right, now, so we can still use Dijkstra's algorithm. It just has to be modified just a teeny bit. Okay, actually, I don't know if it really needs to be modified because we're talking about the adjacent vertices. I guess the only thing we would need to specify is the adjacent vertices that we have an edge that leads to them. All right, so let's go ahead and set this problem up. All right, so this time we only want the route from A to F. So I'm not going to list everything out like I did in my tables up above, all right, because this time I'm looking for one specific route. What's the distance? What's the shortest route from A to F? But I'm going to go ahead and I'm going to use the same algorithm. All right, so I have a 0. I'm starting at A, and all of my other vertices have the weight of infinity on them right now. All right, so A is only adjacent to B. Okay, there is an edge going from A to D, okay, but that is going from D to A. So A only leads to B, so that means I'm going to cross out the infinity, and I'm going to replace that with a 1. All right, and then B goes to C, E, and D. So 1 plus 3, I would change this infinity to a 4. 1 plus, let's see. Hold on, I'm trying to figure out if that 1 is for C to D or for B to E. All right, I'm going to say it goes with both. So B to E, I'm going to say that that's a 1. So 1 plus 1, this is going to give me a 2. And B to D, so 1 plus 2, that's going to give me a 3. All right, so 2, 3. Oh, I should have darkened this one already. All right, so remaining ones that we have 4, 2, and 3. 2 is the smallest, so now I'm going to darken the edge from B to E. All right, so E can go to F. All right, so 2 plus 3, that's going to give us the 5. All right, now technically you think you're going to be done here because A to F, I just crossed out F. However, go through and make sure that there's not another route that's shorter. Sorry if you heard my dog. All right, so 4 or 3 and 5. Okay, those are the vertices we have not yet been to that we have the possibility to go to right now. So 3, 4, or 5, which one's smallest? 3 is. How did we get this 3? Well, that was from B to D. All right, now look to see where can D go. D can go to E. 3 plus 2 would give us 5, so we're not going to change that one. All right, so now we look at all of the other vertices that we haven't yet been to that have a number with them, but not yet a path going there, not yet a darkened edge. All right, so we have 4 and 5. Which one's smaller? Well, 4 is smaller. So now we're going to go back and we're going to darken B to C, which is how we got 1 plus 3 gave us the 4. C leads it leads to E, which 4 plus 4 would give us 8, so we're not going to change this one. 4 plus 1 would give us 5, so we're not going to change this one. All right, which means now, okay, the only vertex that we have that's a possibility to go to, okay, not yet G. Actually, there isn't a way to get to G. All right, the only vertex that we haven't yet been to yet is the F. And so 2 plus the 3 is how we got the 5. So now I'm finally going to darken this edge. All right, and now I'm just going to analyze my results. All right, so now go back and look at the graph and what was the shortest route? What was the path that got us there? Well, how do we get the 5? It was by going A, B, E, F. So we'd list that out, A, B, E, F. And again, that had a total length of 5. All right, and there you go. That is how computers go through and figure out the shortest route from your city to your destination.